Section 3.4, the geometry of linear systems. Let L be the line in R2 or R3 that contains the point x0 and is parallel to the non-zero vector v. Then the equation of the line through x0 that is parallel to v is x equals x0 plus tv, where the variable t is called a parameter. If x0 is 0, the zero vector, then the line passes through the origin and the equation has the form x equals tv. Let W be the plane in R3 that contains the point x0 and is parallel to the non-collinear vectors v1 and v2. Then an equation of the plane through x0 that is parallel to v1 and v2 is given by x equals x0 plus t1 v1 plus t2 v2. So basically the same thing as the line, just add another t v, but since we have two different t's, we call one t1 and one t2, and two different v's, one v1, one v2. So the variables t1, t2 are called parameters, just like the variable t was a parameter. If x0 is the zero vector, then the plane passes through the origin, and the equation simplifies a little bit. If x0 and v are vectors in Rn, and if v is non-zero, then the equation x equals x0 plus tv defines the line through x0 that is parallel to v. So this gives us the equation of a line through x0 parallel to v. In the special case where x0 is 0, the line is said to pass through the origin. The major difference between this definition and this definition that we started with, or rather this theorem, is that this definition that we chose based on this theorem applies to vectors in Rn. So now we have lines for vectors in Rn in general. If x0, v1, and v2 are vectors in Rn, then we can come up with an equation for the plane through x0 that is parallel to v1 and v2. So by starting out with these more specific cases in R2, R3, we've generalized to all of Rn. Now we can do lines and planes in all of Rn. As an example, how about we find a vector equation and parametric equations of the line in R2 that passes through the origin and is parallel to the vector v equals minus 2, 3. So what we can do is, let's pass through the origin, so we'll set x not equal to the 0 vector, and that implies that our equation is just going to be x equals tv. Okay, in this case we have xy is equal to t times minus 2, 3. Just reading off of the vector v that they gave us. So that's our equation. We could also write that as x is equal to minus 2t, because the x component, we could just multiply the t by the minus 2 and get the x equals minus 2t, and we can also get that y equals 3t. So those are the parametric equations. How about we find a vector equation and parametric equations of the line in R3 that passes through the point P0 and is parallel to the vector v. So again, we'll write x equals x0 plus tv. Oops, I wrote tv0, tv. And we've got x, y, z for x is equal to, let's see, we were starting with the point P0 this time, so not the origin, so we'll just throw that in, 1, 2, minus 3. We'll add that to tv, so that's plus t times 4 minus 5, 1, and multiplying out the t, we can get parametric equations. X equals 1 plus 4t, so that's x equals 1 plus 4t, and y equals 2 minus 5t, and z equals minus 3 plus t. How about we use the vector equation obtained in part B to find 2 points in the line that are different from P0. Okay, so how about I set t equal to 1, because the parameter, I could just choose any number to get a different point. And let's see, if I take t equals 1, I plug it in, I get 1 plus 4 is 5. Or I could plug it in over here, it doesn't really matter. Either way, I'll get 5. Plug it in for my y coordinate, I'll get negative 3. And for z, negative 2. To get another point, I could just plug in minus 1. And I would get -3, 7, -4 for another point. How about we find vector and parametric equations of the plane x minus y plus 2z equals 5? Well, we have x equals 5 plus y minus 2z if I solve for x. So why don't I just make y and z parameters? I'll take x equals 5 plus, instead of y, I'll call that t1. And instead of z, I'll subtract 2 times t2. So just subtracting 2z. So I'll get that y is my parameter t1 and z is my parameter t2. Okay, so that means that my vector equation is xyz equals 5 plus t1 minus t2, comma t1, comma t2. We can then separate the equation out by writing xyz equals 5, 0, 0. Because there's a constant term of 5 here, you could write this as 0 plus t1, 0 plus t2. So my constant coordinates are 5, 0, 0. The coefficients for t1, well, there's 1 t1 over here, 1 over here, and 0 over here. So I could take t1 times 1, 1, 0. And then I've got minus 2 t2 over here, 0 t2 over here, and 1 t2 over here. So plus t2 times minus 2, 0, 1. Next, let's find vector and parametric equations of the line through the origin of R4 that is parallel to the vector v. So again, we'll write x equals tv. We don't need x naught because it's just the 0 vector anyway in this case because we're at the origin. So that's the same as saying x1, x2, x3, x4 for my vector x is equal to t times the v they gave us, which was 5 minus 3, 6, 1. Parametrically, that could be written as x1 equals 5t, x2 equals negative 3t, x3 equals 6t, and x4 equals t, 1t. Oh, I accidentally wrote tt. That should really be a 6t. There, that's a little bit better. How about we find vector and parametric equations of the plane in R4 that passes through the point x0 and is parallel to both v1 and v2. So we will write x equals, so in this case they gave us an x0, we're not at the origin, so I'll have to use it, plus t1 v1 plus t2 v2. And I could write x as x1, x2, x3, x4 equals, let's see, x naught is 2 minus 1, 0, 3, then plus t1 times v1, which is 1, 5, 2 minus 4, and t2 times 0, 7 minus 8, 6. Parametric equations would therefore be x1 equals 2 plus t1, x2 equals minus 1 plus 5t1 plus 7t2, x3 equals 2t1 minus 8t2, and x4 equals 3 minus 4t1 plus 6t2. If x0 and x1 are distinct points in Rn, then the line determined by these points is parallel to the vector v equals x1 minus x0. So it follows the line can be expressed in vector form as x equals x0 plus t times x1 minus x0, because this vector v can be any parallel vector. So we could factor out the x naughts and get 1 minus t times x naught plus tx1. So I'm basically distributing the t's and then factoring out the x naughts. These are called the two-point vector equations of a line in Rn. How about we find vector and parametric equations for the line in R2 that passes through the points P and Q. So we'll write x naught equals RP, so that's 0, 7. And x1 will equal Q, so that's 5, 0. So then we have x1 minus x naught is equal to 5 minus 7, and that gives us that xy is equal to 0, 7 plus t times 5 minus 7. So parametric equations are x equals 5t, y equals 7 minus 7t, and therefore we get the line y equals, well, if x is 5t, that means that x over 5 equals t, so I'll plug that in for t. So I'll get 7 minus 7 times x divided by 5, which I could just multiply everything through by 5. I'll get 5y and 7x, move the 7x to the other side, so I'll get 7x plus 5y equals 35. Because if everything gets multiplied by 5, so does that 7. But I could also do this by writing x naught equals 5, 0 for p, x1 equals 0, 7 for q, and write xy equals 5, 0, the x naught, plus t times minus 5, 7, which would give me parametric equations x equals 5 minus 5t, and y equals 7t. So then I would get x equals 5 minus 5 times y over 7. So I'd get 7x plus 5y equals 35, same as before. So it doesn't matter which form of the equation the way we actually use, as long as we plug everything in correctly. If x naught and x1 are vectors in Rn, then the equation x equals x naught plus t x1 minus x naught for t between 0 and 1 defines the line segment from x naught to x1. So what we're doing is we are cutting off our line for these t values. We're not going to go anything below 0, we're not going to go anything above 1, so we're only going to get a piece of the line. When convenient, we can rewrite this equation. Again, distribute the t, factor out the x naught, you get 1 minus t times x naught plus tx1, where t is between 0 and 1. So how about we do a quick example? Let's find equations for the line segment in R2 from x naught equals 1 minus 3 to x1 equals 5, 6. So we get x equals 1 minus 3 plus t times 4, 9. And 0 is less than or equal to t is less than or equal to 1. So that's from our first equation, where I subtracted x1 and x naught in order to get 4, 9. How about I write it the other way now, where I use the 1 minus t. So that would be 1 minus t times 1 minus 3 plus t times 5, 6. So I kind of like the second equation a lot because it doesn't actually require me to do any of the subtraction when I write it. If A is an n by n matrix, then the solution set of the homogeneous linear system ax equals 0 consists of all vectors in Rn that are orthogonal to every row vector of A. So we're basically switching gears here by saying that if you look at each of the rows of A, those are just going to be a whole bunch of different coefficients. You can imagine them multiplying by the columns of x to equal 0 in the homogeneous linear system ax equals 0. So that means that, for example, the first row of A is, let's say, r. So r times the columns of x has to equal 0. You could say that's just, let's say, r1 for the first row. That's like saying r1 dotted with x has to equal 0. Or the number 0, because it's a dot product. But r2 dotted with x also has to equal 0, etc., all the way down every single row of this system in order for this to be true. That's what matrix multiplication is. It's a dot product along the rows. So that means that every single one of these rows is a vector that's has got to be orthogonal to x, because that's what it means when the dot product is 0. So that's basically what our theorem is. So how about we apply that to an example real quick. We will basically show that theorem 3.43 is true for this system, which we already solved previously. So what we'll do is we'll write out our vector x. We already have the solution given over here for each of the components of x. So we can write that as minus 3r minus 4s minus 2t, r minus 2s, s, t, and 0. And our first row is 1, 3, minus 2, 0, 2, 0. All I did was read off the first row. My second row is 2, 6, minus 5, minus 2, 4, minus 3. My third row is 0, 0, 5, 10, 0, 15. And my fourth row is 2, 6, 0, 8, 4, 18. So how about I take R1 and dot it with X. I'll get 1 for my first component of R1 dotted with this guy over here. So that's 1 times minus 3R minus 4S minus 2T. And I'll add that to 3 times R plus negative 2 times negative 2S plus 0 times S plus 2 times T plus 0 times 0. Notice we get tons of cancellation. All of the terms end up canceling each other. We end up with 0 for that dot product. This has to be true for every single row, so let's take a look at R2 dotted with X. We'll get 2 times minus 3R minus 4S minus 2T plus 6 times R plus minus 5 times minus 2S plus minus 2S plus 4T plus negative 3 times 0. And that'll also be 0. Again, tons of cancellation. For R3 dotted with X, we get 0 times minus 3R minus 4S minus 2T plus 0 times R plus 5 times minus 2S plus 10 times S plus 0 times T plus 15 times 0, which is also 0. And last but not least, we'll check R4 dotted with X, which is 2 times minus 3R minus 4S minus 2T plus 6 times R plus 0 times minus 2S plus 8 times s plus 4 times t plus 18 times 0. Again, 0. Exactly as we expected. The general solution of a consistent linear system, ax equals b, can be obtained by adding any specific solution of ax equals b to the general solution of ax equals 0. So that's kind of cool. If we want to get the general solution of a system that equals some vector b, then we can just add any specific solution we manage to find to the general solution of ax equals 0, and it'll give us the general solution. Let's prove this real quick. How about we let x naught be any specific solution of ax equals b? And we'll let, basically we're saying, like, if we have something in terms of some parameter, like t, x naught could be a solution where t equals 1. We'd like to be able to get the general solution where t could be anything. So we'll let w denote the solution set of ax equals 0, and we'll let x naught plus w denote the set of all vectors that result by adding x naught to each vector in w. We must show that if x is a vector in x naught plus w, then x is a solution of ax equals b, and conversely that every solution of ax equals b is in the set x naught plus w. Okay, so first let's assume that x is a vector in x naught plus w. This implies that x is expressible in the form x equals x naught plus some w vector, where ax equals b, x naught equals b, and aw is equal to 0. Therefore, we have ax equals a times x naught plus w, distribute the ax naught plus aw, but ax naught is b, aw is 0, so ax is equal to b. So that means x is a solution of ax equals b if x is a vector in x naught plus w. Now, let's let x be any solution of ax equals b. To show that x is in the set x naught plus w, we must show that x is expressible in the form x equals x naught plus w, where w is in w vector is in capital W, which is the same thing as saying that aw is equal to 0. We can do this by taking w equal to x minus x naught. Obviously, if we plug in x minus x naught, the x naught cancel and just gives you x. It must be in w, since a times w is a times x minus x naught. Distribute the a's again, you get b minus b, which is 0.